Hello, I'm Rod Elmore, and today we have a very interesting topic. When I first saw this as a student, I thought, these people are going out of their minds. But then all of a sudden, as you're going to see when we're done, that it's actually useful. It's like they made something up out of nowhere. So first what we're going to do is some matrix arithmetic. So we already know what a matrix is, or should know, but a matrix is a rectangular array of numbers. For example, we could just have, and usually we let matrices be a capital letter. So matrix A, we could call this rectangular array of numbers where A, B, C, and D are any rational numbers. So now we have a matrix A. I'm going to put up here a matrix B. And we're just using letters for the numbers. Now what we want to do is we want to develop an arithmetic. So let's see, what do we have in arithmetic? We have to be able to add. So we'd like to be able to add these matrices. Well, how do we add A plus B? Well, just how would you think you might do it? Well, you might do it just that you might add A onto E, B onto F, C onto G, and D onto H. Well, that worked out pretty good, so that's the way we would add them. A plus E, B plus F, C plus G, and D plus H. And that's exactly how we do it. Now, since add and subtract are very similar, just adding the inverses, this works also for subtract. So then what other operations do we have? We have multiply. So how can we multiply a matrix? Well, we can multiply a matrix by what we call a scalar. This is a scalar, a single number, and we can multiply a matrix that way. And I think intuitively you're going to guess how you're going to do it. You're going to multiply n times A, and you're going to get NA, n times B, and we're going to get NB, n times C and get NC, and n times D is ND. Now you got to realize they're just making this stuff up out of our head. Is that how it's going to work for us? It is, but it might not work and it might be useless and we'll never do this again. But it did turn out to be useful. And so what we have got now is we've got add, subtract, multiply by a single number. And now what next do you think we should do? Multiply two matrices together. Okay, so how do you think the two matrices are going to look if we multiply those? I think if we did it intuitively, it'd be A times E, B times F, C times G, oops, D times H. Okay, that would make a lot of sense. Okay, what we figured out is when we add like this, multiply by a scale like this, we multiply like that, this whole thing is totally useless, so we might as well just forget about it. There is no value to it. So we've got to change something. So what we figured out is kind of a real odd thing. When we multiply these two, this is what we're going to get. And this is the hard one, not this common sense. When you multiply A times B, this is what you're going to do. You're going to multiply this row times this column, the individual components, and then add the two products. So let me just write that down. So it's going to be A times E plus B times G. Now that doesn't make any sense, but what that does, it's useful. A whole system is set up. And so it's kind of nice. It just works. So now let's do the second one. A, B row times the column, and where they intersect is where that goes. So A times E, be AE, B times, let's see, got that wrong. Row times column, this column. A times F, that's why it helps to point. B times H, this row times this column. Okay, now this row times this column would be down here, so that would be CE plus DG. And then this row times this column would be CF plus DH. So that's how we multiply. a real strange way, but it's the way that makes this whole thing useful. So now how do we divide? That's the next operation. Well, if this is how we multiply, there's no way you're going to divide. So we're done dividing. Now we could divide by a scalar by making this a fraction, but that's incidental. So now I want to practice these three things. And mainly this is the hard one. This is the hard one. So let me erase these two. These are pretty common sense. We've got that to look up at there. Let's come up with an actual matrix. So I want to multiply matrix 2, 1, 4, 0 times, well, let's add them first. Negative 3, 1, 4, 5. Now let's get rid of that duplicate there. We'll put a 6 in there. Now we want to add these together. Well, if we add them, we just add them component to component. So this would be 2 plus a negative 3, be a negative 1. 1 plus 1 would be 2. 4 plus 6, 10. And 0 plus 5, 5. So that's pretty straightforward. But now let's do that over there. That's the fun one. Okay, now we're going to multiply this row times this column. When you get pretty good at this, you can just do it in your head. But let's just go kind of slow here. So it's going to be this number times this one. And you have to do this. Watching me do this is pretty useless. So you got to try this after I do it if you haven't done it. 2 times a negative 3 is a negative 6, plus 1 times 6 is 6. Now this row times this column, 2 times 1 is 2, plus 1 times 5 is 5. Now I'll go a little slower here. This row times this column, 4 times a negative 3 is a negative 12, plus 0 times 6 is 0. Now this row times this column, 4 times 1 is 4, and 0 times 5 is 0. So that's our result. So what's our result going to be? 0, 7, negative 12, and 4, if I did everything correctly. And we're going to assume I did. 2 plus 5, negative 12 plus 0, 4 plus 0. So this is the product of these two matrices, using this very unique and I admit very strange tool here. So we've got, and you can do the, try some of the other ones. Now what we need to do is think about, in our arithmetic, we have two very special numbers. And we need those numbers in this arithmetic, otherwise you wouldn't have multiplication and addition. What we have to have is this kind of a thing. In our arithmetic, we do have a number that does this. So for example, 2 plus something equals 0. What is that thing we can add on to 2 to make it go away and get our identity, our additive identity? And that would be what, a negative 2? And likewise, 3 plus something equals 3. What would this have to be in our system? Something you add to something, not change it. Well, it's that 0, isn't it? So we've got to find this 0. We've got to find these negatives for our arithmetic. So what could we do? What would a negative be for this one? So it would work here. Well, let's try an actual number. 2, 4, 3, 1. What could I subtract from, or add to that? Now, what would be my, I have to get my identity, my additive identity. That's pretty intuitive. Which 2 by 2 matrix would that be? 0, 0, 0, 0. So what could I add to that? Well, it's pretty straightforward. It's really the additive inverse for these. So this would be a negative 2, negative 4, negative 3, negative 1. Boom, we got the 0. Now, does that 0 work if we do this thing with it? Let's try it and see. Now, these all seem pretty basic, kind of silly we're even doing them, but I think it pays to do the easy ones before you get to the hard ones. Now, if you add this to this, does it not change it? It obviously doesn't change it because we go 2 plus 0 is 2, 4 plus 0 is 4, and 3 plus 0 is 3, and 1 plus 0 is 1. So we found our 0. So the 0 of our system is 0, 0, 0, 0. That's our additive identity. And the negatives works here. So that's not a problem. Now let's look at this other one. Here's the other property we have to find. We do have a number that when we multiply it times 3, it gives us 3. And what's our number in our system? It's just a 1. So what we need is, we need to find that 1 in our system. We found the 0. And the other thing that we need to find is something times this that would give us 1. And what in our system, when you multiply it times this, will give you 1? Well, you might think it's 1/3, because 1/3 of 3 is 1, but we don't have divide, you got to remember. So do we have something where we don't need divide? Well, we never need a divide. Dividing and subtracting is for the grade school people, really. We never needed those, but not for mathematicians. What we could have used here is 3 to the negative 1. Because remember, the negative there means 1/3. And then this is to the first power. So if we were to do those in our system, what would we get? 3 to the first times 3 to the negative 1. We add exponents when we multiply. We get 3 to the 0. We already learned that 3 to the 0 is 1. So this is what we need to get. We need to get the multiplicative inverse and the identity element for multiplication. So what would those be? Well, let's track those down. Let's try 2, 1, 4, 5. Now, is there a number that we could multiply by this and not change it? Remember, that's what 1 did. Is there a matrix that we can pick here? Well, if you think about it, the matrix would be 1, 1, 1, probably a guess. Does that work? Well, it's got to give me a 2 right here, right? Let's just try that down here and see. 2 times 1 is 2. 1 times 1 is 1. It gives me a 3. So right away it fails. So that's not it. Well, what we really got to do is wherever the heck this 1 came from, well, that came from here. So how about if we make that a 0? Then that one would work. Now let's try this times the second one. 2 times this column is supposed to give us this one. 2 times 1 is supposed to give us this one up here. 2 times 1 is 2, and 1 times 1 is 1. So we're going to end up with 3. We don't want that. So what we have to eliminate is probably this one so it doesn't duplicate us. Now let's try it again. 2 times 0 is 0, plus 1 is 1. So that works. Now you got to try this yourself a little slower. For this one times this one. Now this is where we ended up to make the top row work. Let's see if the bottom row will work. It'll be 4 times 1 is 4. 5 times 0 is 0. So we're going to end up with 4. That worked. This row times this column. 4 times 0 is 0. 5 times 1 is 5. So it's just a 5. So we get 2, 1, 4, 5. So this is our 1. So our 1 in our system is a little different than we thought, but that works out pretty good. Now next, what other number do we have? Well, we have that fraction problem. And so what we had was, if you take a number 3, for example, you multiplied it by something, and you got 1. This had to be that 3 to the negative 1. So that's what we're after now. This is our last thing. In other words, a reciprocal is something. It's called the multiplicative inverse. So now we're going to take a number. Let's go with 3, 2, 5, 1. We want to multiply a matrix times this. That'll give us our 1. This is the harder one to do. So what what matrix could we multiply times this to get me that? Well, it's a difficult one. If it's any large one, we'll use our calculator to find it. But here we're got a little formula, and I expect that you can use the formula even though you've never done it before. Let me show you the formula. The inverse of A, this one, is equal to 1 over AD minus BC. This is not supposed to make any sense. This is a formula where you get to do a little monkey see, monkey do math. And then we're going to flip these around for no reason, except I know that's the answer. We're going to put a negative in front of these two, and I'm telling you that that little formula will always find you the inverse of it. It does. We can prove this, but that's not the scope of what we're after here. So let's see if we can figure this out. Now, some of you who are on top of stuff, really sharp mathematicians, would realize what number don't we want this to be? If this was a 0, we'd be all done. Well, that sometimes does turn out to be a 0, and when that happens, that means the system will not work. So you've got to have that not be a non-zero number. So now let's use this formula to find this number that when you multiply it times this one will give you our 1 in our matrix system. So let's see how we can find this. First, we got to find this fraction. And this fraction says A times D. 3 times 2 is 6. C times B. 1 times 5 is 5. Now, I made this one turn out real sweet. 6 minus 5 is 1, and 1 into 1 is 1, so this has kind of gone away. Now, these have been flipped around, 2, 3. These have negatives in front of them. So I'm saying that's my number. If this was still a fraction, we'd have to multiply that through and get that. But let's see if this works. 2, negative 5, negative 1, 3. Now, you'll be given this formula that we had here, this formula here on the test, to be able to do this. If it's bigger, you'll just use your calculator. Machines can find it very quickly for any of them. So now let's see if it works. Now remember how we do this. This row times this column. I'll go a little slower here in this. 2 times 3 is 6. 5 times a negative 1 is a negative 5. 3 times a negative 5 is a negative 15. 2 times, let's see, 5 times 3 is a positive 15. This row times this column, 1 times 2 is 2, plus 2 times a negative 2 is a negative 2. This row times this column, a negative 5, and 2 times 3 is 6. And when we add these together, what do we get there? We get a 1. We add these together, we get a 0. We add these together, we get a 0. And we add these together, we get a 1. So it did work. A little complicated. If you put this into your calculator, it will find that inverse for you. But you should be able to do it for a 2 by 2 matrix by yourself. So now we've developed all the arithmetic that we have in our system. The only thing we don't have here is divide, because there's no way to practically divide. So now you should try some problems on your own, because watching me do them doesn't really help. You got to watch somebody, and then you got to do it yourself. So try the video homework and the other homework in the class until you figured out how to do this yourself. Thank you.